Okay, let's keep going. I'm sorry. For the for this spectrum. I put the wrong figure. Okay, now let's consider a little bit complicated case, which is the you have two lines here. Okay, at 2 and 8 wave number, and then by doing the Fourier transformation, and then you get this more complex interferogram. Okay, and then this interferogram can be expressed by these two terms. Okay, p1 term and p2 term. Of course, here delta nu bar 1 and nu bar 2 is different. Okay, this is also a very simple case. Okay, and then inverse Fourier transformation, this interferogram gives this spectrum. Okay, in this case, yeah, p1 is 1 and p2 is 2. P21 is also 1. Okay, and nu 1 is 2 inverse centimeter, and nu 2 is 8 inverse centimeter. Okay, yeah. And here, what is the lambda 1? Okay, so lambda 1 is look at that, 1 over 8 is 1 over 8 centimeter. Lambda 2 is 1 over 2 centimeter. Okay, this is also a simple illustration of FTIR, yeah, Fourier transformation and inverse Fourier transformation. Okay, the third example is more complex case. Okay, let's consider your original spectrum is like this one. Huh? Now it looks like a spectrum at this wavelength, and then Fourier transformation gives this interferogram. Okay, so when you obtain this interferogram and then you do the inverse Fourier transformation to get your original spectrum. All right. Then what about the more complex case? That's figure D, and this one. Now you have two peaks here and there. Okay, here. All right, and then you get more complex interferogram. But idea is to do the inverse Fourier transformation to get this one. Okay. Now you understand. Yeah, you are beginning to understand. I hope. All right. So idea is that in this interferometer, you put your sample here. Okay? Of course, you can put your sample maybe in this position, but usually you put your sample here. Okay, between this beam splitter and the detector. Okay. Okay, this is actual configuration of the inside FTIR. Okay, but this is not the only design, but there are several different designs. But this is, I think, the most commonly used design for FTIR. Okay? Here is the interferometer. Okay, and this IR source, and then you send it IR beam through here, and then here is a beam splitter, the mirror here, and then let's see, where is the um, moving mirror maybe around here. Okay, okay, this is interferometer. uh, okay, and then interference pattern now eventually goes to a detector. Okay, through this sample. All right, and then all this wavelengths is controlled by this very precise laser. Okay? That's another advantage of FTIR. Okay? So an interferogram of a reference sample containing the cell and the solvent is first recorded. Okay, as you know, this Fourier transform spectrometer is a single beam instrument. Okay, so you have to first measure the spectrum reference interferogram, right? And then you put here the sample first, reference here and then sample here, and then you can subtract. Okay? I'm sorry, not subtract, the quotient, okay, of the sample spectrum divided by the reference spectrum is the transmission spectrum of the sample. Okay, yeah. So here the resolution of this FTIR is given by this one. This equation 1 over delta. Here is a delta is a maximum retardation. Okay, but as you see, the resolution of this FTIR is much better than any dispersive spectrometer. Okay, that's why this FTIR gives you a very detailed spectrum. Okay, even with this FTIR, you can differentiate the rotational or energy levels. Right? Okay, now it's a real experiment, real the sample, right? This upper figures are interferograms. Okay, and let's see. So first you observe the reference interferogram like that. Yeah? Now this is a typical shape of interferogram, right? And then inverse Fourier transformation gives this kind of spectrum, right? So this one include the light source, spectrum, and all other things. Okay, it contains everything, all right? And then you put sample in the sample position. Then you get the sample spectrum, sample interferogram, right? Now you get this type of interferogram, right? At first, they are they look similar, okay, and then only from this interferogram, it is impossible to you know know what the actual spectrum looks like. Okay, how do you infer this spectrum from this interferogram? Right, it's impossible. All right, but after inverse Fourier transformation, you get this spectrum. But this spectrum is rather, it is not flat. Why? Because it contains also this reference spectrum. Okay, so you divide this one by this one. Okay, and then you get very, standard looking this spectrum, the IR spectrum. All right. For a special range of the delta nu bar, points must be taken at retardation interval of this is a retardation interval. Okay, delta nu bar is a spectral range. Okay, so whole spectrum, for example, let me see. This is around wave number is from 4,000 down to 400. Okay, here is the calculation. If spectral range is 4,000 wave number, right? Yeah, and down to the zero, right? That is the ordinary case for for infrared spectroscopy, and sampling interval with delta which is retardation. Let's see, that is 1.25 micrometer. Okay, and mirror motion is one half of this retardation, all right, which is 0.625 micrometer. Okay, so usually the mirror is moving only one distance. Okay, this is a mirror moving distance. Okay, and how many data points? You see, 1 centimeter divided by this number at 0.625 micrometer, and then you get 16,000 data points. All right, 16,000 data points. Wow, this is a lot. This is a lot from here to there. 16,000 data points, and then now we have a very big problem, which is that how do we perform this inverse Fourier transformation, okay, to get this spectrum from this interferogram, right? Yeah, we have theory, which is a Fourier transformation. Okay, he already proved that any function, right, can be expressed by uh, the sum of sine and cosine terms. But how? We have to do that very rapidly. Okay, and very fortunately, in the 1960s, two mathematicians, Cooley and Turkey, they developed fast Fourier transformation. Okay, which is called FFT. Okay, I didn't the right here FFT. Okay, by doing that algorithm, it's now very very you can do the inverse Fourier transformation very fast. Okay? Yeah. That algorithm is amazing. Yeah. Okay, yeah, that's the basic idea. All right, for FTIR. Okay.